Hello everyone. In this video, we will talk about virtual memory, and we will have a couple videos to finish the basic topic of virtual memory. This is also required for your final exam. It is a really important concept for high-level computer architecture design. Also, I would like to mention, if I have time this week, I will record a small video, but that's not required to demo how you could use the Mars simulator to simulate different types of cache. So simulate the performance, simulate the cache performance and evaluate the cache performance using the simulator. So as we have canceled the last lab, for cache topic. So you have only one quiz for the cache topic, but the cache topic is really important computer organization design topic. So I would like to show you how to use the simulator to simulate cache. So for this video, for virtual memory topic, for week 14, we will focus on virtual memory topic. So if you still remember, so we have been introducing the structure of how to design or more efficient pipeline processor. And we have discussed about that different types of hazards like data hazards, branch hazards, and how to improve the performance, the efficiency of a pipeline processor. So the pipeline processor is the most important parallel processing concept. So we are actually dealing with parallel processing and how to perform the branch prediction, forwarding, instruction reordering. All those techniques, they are parallel processing technique. They are parallel processing technique. So after this week, for week 15, we will have a little bit review. I will give you a little bit more information about how the final exam will look like, and also I will also talk more different types of parallel processing parallel processing technique. Okay, in week 15. So this week we will focus on virtual memory, which is another really important topic for high-level computer architecture design. So as you may still remember, when we talk about the computer design, we spend a lot of time in the center part, which is the CPU, the heart of the computer. And then we also introduced how to design a cache, different types of cache memory. And then, the most important memory, the primary storage for the whole computer is the RAM, the main memory we're using most of the time, right? So when we say memory, then we basically refers to the RAM, the main memory, which is connected to the CPU. However, we never think about, well, you do have the hard disk, and then how, so of course, if you have a really small RAM and it is not able to hold everything, right? So you might have something have to be stored in the hard disk. So and also, so the RAM is of course only storing the data we need to use when we run the programs, right? And all the other files, they're actually permanently stored in the hard disk, And the RAM is just temporarily holding the data we are actually using when we run the program, when the program is being executed. So today we'll talk about virtual memory, which is the really important technique to combine all the basic things we have learned about memory. So we of course know how to use the RAM, the main memory. However, how to include the hard disk and to make the whole memory system, and that is today's topic, virtual memory. So we need to understand virtual memory. So first of all, so the virtual memory slide. Actually, I use a lot of the material come from this reference tutorial. So it is a professor from another university, pretty good in this topic. He has like really good YouTube videos and reference material and some exercise problems for virtual memory topic. And you could also check the interactive lecture he has, and this is the key code if you would like to, but you don't have to. So those are like the reference material I use for this slide. So if you prefer to watch the whole, more information and some more examples related to virtual memory, so that's not required, but you could if you're interested in watching more material topic related with virtual memory, then you can check out this YouTube link to watch some of his videos, and you can even check the interactive lecture open source, those public material online. So first of all, what is virtual memory? Why we want to introduce virtual memory? So I don't know how many of you have thought about this question. For example, so if I have like a 4 GB, 8 GB RAM installed in my computer, sometimes I may need to run a really huge program. And how about if you run out of RAM? And if you do not have enough memory, then what will happen? Or if you have multiple programs, they're running together, and then each program might need a lot of memory, and then how can you organize them? Are they using the same piece of memory? Are they actually accessing the same piece of data? How can we manage those things? So all those problems are actually the problems for using RAM. And we didn't even talk about any of those things before. So actually, all those things are the problems we need to solve for to make a real computer, right? And then the technique we will be using to solve those problems is called virtual memory. So what is virtual memory? By looking at the term virtual, then you know this is not real. So it is actually performing a mapping, or you could say, oh, this is kind of like an indirect mapping. So you're not, so when you try to use the RAM, then you might need to check certain mapping, and then the program does not need to worry about which piece of memory you are using. So even you run out of RAM, you could still have, some other storage location like the hard disk to hold your data. So how can we do this? All those questions we'll look at how to solve all those questions. So first of all, in general, there are three problems using the RAM. The first one is if we do not have enough RAM. For example, so each different computer has different size of the RAM, right? So my computer has 8 GB. This one has 16 GB RAM. So your laptop may have 8 GB RAM, and some other small laptop has 1 GB RAM. It could be also possible. So suppose you have only 1 GB RAM, and then your program need more than, so to simply run a single program, that program actually needs 2 GB RAM memory storage. And then how can we do that? So it is a big problem, right? So of course, the hard disk you have, the RAM, the RAM memory chip you have installed in your computer is a fixed size, right? However, your program requirement can be anything. The requirement of your program can be anything, can be any big, right? So of course, if you do not have enough memory, this will cause problems. So that's the first problem we need to think about. The second problem is you might have holes in the address space. So what does that mean? So for example, what does the hole mean here? So for example, if I have a program 1, program 2, program 3, three separate programs, and the first program want to use 1 GB memory. The second program wants to use 2 GB memory, and the third program want to use 2 GB memory. So altogether, you need 5 GB memory. However, in your hardware, in your processor, you only have 4 GB memory installed. You only have 4 GB RAM. So if that's the case, suppose the first program is using the first 1 gigabyte, and the second program is using the second and the third gigabyte, right? And the third program would like to use 2 gigabyte. However, there's no enough memory right now, and maybe the first program is done, for a couple after a few seconds, then the first program is done, so you don't actually need that 1 gigabyte anymore. So we could release the 1 gigabyte required of the first program. We can release that one because the first one is finished, right? So however, even you have the first gigabyte and the last gigabyte available in your memory space, your program 3 cannot use it because it is separate pieces, right? So there are 2 separate pieces of memory location, even it is 2 gigabyte, but they're not connected. So how can your program, use those separate address locations? So that's a big question we need to answer. So the third problem can be, how do we keep the program secure? So what does that mean? For example, so the first program 1 would like to get access to the memory address 1024. And the second program also want to use the data in the memory address 1024. And suppose they want to use them together. So they want to use this piece of memory address. They want to use the data in this location. So both of them want to use this piece of data. Then what will happen? So the first program might want to update the memory address 1024, and the second program might just need to read from that location. And if you have one is reading, one is writing, and then suppose the second program would like to read out the original data, and the first program just updated that piece of data, so it will of course cause a lot of problem, right? It will corrupt or crash. So those are all the important problems we actually did not answer, or we actually didn't even think about that before when we try to introduce the basic structure of the computer. Then we only understand how the CPU uses the RAM, how the CPU uses the cache, and how the cache could serve as a second temporary storage to speed up the memory access. However, there's a lot of other problems we have to think about, like the 3 questions we just discussed. So how can we solve those problems? Then the answer will be we have to do virtual memory instead of a real memory space. So because each piece of program always assume we have 32-bit memory address, right? So when we write our assembly code in the previous labs, and we always assume the address is 32-bit memory address. What does that mean? If you have 32-bit memory address, that actually means you have 4 gigabytes, right? So 32-bit memory address means we have 2 to the 32 different byte location. We have 2 to the 32 byte location, right? And then we have 2 to the 30s. We have 2 to the 30s words locations inside of the memory, right? So that actually means we have 4 gigabyte space inside of the RAM, right? So I hope everybody know how to calculate this, right? So we have mentioned this for quite a few times. So 32-bit address actually means you have 4 gigabytes. Different locations. So inside of the memory. However, it is not always true. You can always have 4 gigabyte memory address. And most of the recent laptop computers we're using, most of them have higher than 4 gigabyte. And a few years ago, that a lot of the I can't remember. I think 4 or 5 years ago, at that time, the laptop I was using has 4 GB memory. So so you sometimes have a bigger RAM installed, sometimes you could have a smaller RAM installed, but your program always assume there's 4 GB in the RAM. Your program always using a 32-bit memory address. So what does that mean? That actually means probably, we don't have to tell the program which piece of data you are actually using, and the program can always assume there is a 32-bit memory address, and there are 4 GB memory locations in the memory. So what we could do is we can do a mapping. Between the program and the real memory locations, between the program and the RAM. And this is called virtual memory space. This is called virtual memory. The technique here is called virtual memory. So it is actually trying to map the program's memory to the real physical memory. So each program always see 4 GB. And each program always assume there are 4 GB for this program to use, and the address is always 2 to 32 bits. However, the real physical address, it is actually using, depends on how you do the mapping. So the program is actually using a virtual memory address. And what it is really using, it is actually the physical memory address. So how this will look like? I try to switch to my iPad, but seems like the slide format, this one I created, has a little bit problem, so I have to stay in my laptop, which is weird, but it's okay. So if I need to draw something, I'll switch to the iPad and pause a little bit and switch again. So what is virtual memory? So we actually need to add a mapping, right? So because directly using the real RAM, cannot solve all the problems. So we have to add a mapping layer between the RAM and the program. Suppose a program would like to use the 32-bit address, and the program, it is always assuming that there are 4 GB inside of the RAM. So it doesn't actually need to know. So the program actually does not need to know how many different addresses, how many different locations there are in the RAM. So the program always assume there are 4 GB in the RAM, and then whatever data the program would like to use, it will refer to the mapping table. So there is a table performs the mapping between the program and the real RAM. And suppose there are not enough space. Inside of the real RAM installed. So for example, you have only 1 GB real physical RAM, and then the program needs some more data. So of course, you could use the hard disk, because the mapping will map some data into the RAM and map some data into the hard disk. So the virtual memory technique, virtual memory technique, helps us to give us some flexibility in how we could use the RAM. Give us some flexibility in how we can use the RAM. For example, suppose we have a program would like to use the data 0, 1, 2, 3, 0, 1, 2, 3. So we want to use four pieces of data. the program would like to use the address 0123, address 0123. So it always assume there, each address is a 32-bit long address, and then it will check the mapping table, to look at where is my first data, second data, and third data, and fourth data. So the first three data perfectly mapped to the RAM. So you could get the first three data from the RAM. You can get the first three data from the RAM. However, suppose your RAM does not have any more space, and then we have to use a low-bay hard disk. So how can we use hard disk? How can we make this kind of usage? Of course, we would like to be really efficient. Right? So remember that your hard disk is really far away from the RAM, and get access to the hard disk is much slower than the RAM, right? So if you have a really big RAM, of course it's good, but sometimes you don't. So suppose we do not have enough space. Right now in the RAM. So what we can do is, for example, the first piece of data has the name program 0. So the first piece of data is actually, we finished the usage of the first piece of data. After we use data 0, data 1, data 2, after we use data 0, data 1, data 2, and the first piece of data is done. So we don't actually need it anymore. We do not actually need it anymore. So what we can do is we can move that piece of data. Well, you cannot just throw it away, right? So you have to keep it somewhere. However, the program need to use the data, last piece of data 3, which is the last piece of data. It is not in the RAM. So it could be actually in the hard disk. Right? So suppose we would like to use it. So you do not want to put it in the hard disk because later on you may want to use it again and again. So what we can do is we can put the data which is not really used not really often. So for example, suppose the first piece of data, which is called program 0. So the first piece of data is not needed anymore. So we can put that piece of data in a hard disk. And we can put the recent used data, like program 1, 2, 3. So the second, the third, and the fourth piece of data, we can put those data in the RAM, right? So you only have 1 gigabyte. You have 3 different locations, but you need to hold 4 pieces of data. But you could, of course, select 3 of them and put them in the RAM, and you can put some data which is not that often used in the hard disk. You can put some data which is not that often used in the hard disk. So what does the mapping do here? The mapping need to keep records that where is your data A, data B, data C, data D. So where is each piece of the data? In reality? Where is their physical location? Where is the physical location of each piece of data? So as long as you know where they are physically, then you will be fine, right? So in order to organize, use all the storage, including the hard disk and the RAM, then we could use virtual memory technique, which is simply add a additional layer, such as a mapping table, to manage where they are physically, And then the program always see a 32-bit long address because the program always assume there's 4 gigabyte address, 4 gigabyte locations, memory storage. So a quick, simple question. So what is going to happen if the program performance when the data it needs is on the hard disk or not in the memory So what does that mean? So if the data the program needs is not inside of the RAM, it is actually in the hard disk. So what will happen? you will have better performance? Of course, no. You will have nothing will change? Of course, no. So you will have worse performance. This is true. So we, of course, will have bad performance because if you want to read something from the hard disk, it is much, much slower than the RAM. Remember, it is far away from the CPU, and it is made by cheaper material. So it's magnetic material. It's not really a piece of circuit, to be honest. So to read a piece of data from the hard disk could be even more than 1,000 times slower compared with reading from the RAM. So we would like to know this as a common sense, okay? So reading from the hard disk can be more than 1,000 times slower than reading from the RAM. So that's the reason why you always want to have a big RAM, which is more expensive, right? So of course it's better to guarantee your performance, but it is more expensive as well. So how to solve the second problem we have just discussed, the holes in the address. So for example, so we have 1 GB on the top, 1 GB on the bottom, but there's another piece of program would like to use both of those. So because this program 3 requires 2 GB. So they are not connected. And when you program your assembly code, if you still remember, then you don't actually know which piece of where the data is. And if you have a big array, so you have a really big array, and that array costs a 2 GB memory. So of course they should be connected. When you look at the program, when you look at the address inside of the program, all the address, they should be connected. It should be the continuous address. However, in reality, they could be far away from each other. So now, if we have the mapping, the virtual memory technique, then of course we are able to solve this, because you can map each different memory address to wherever you want. And as long as they are mapped to a certain location, then the program will be able to run. So then, such as we could have a mapping. We could have a mapping table, and then the mapping table actually put the first half of the 2 GB on the top location, put the second half of the 2 GB on the bottom location. So that will perfectly solve this problem. And then the third problem we had is how can we keep the program secure? So suppose they would like to read the same location. So the first program would like to read memory address 1024, and the second program also want to read the memory address 1024, for example, or one is trying to read, one is trying to read to the same location. Then what will happen? So suppose we have the mapping technique, virtual memory technique. So the program address maps to the RAM address. So what we are actually using, the 1024 for program 1, the 1024 for program 2, will be actually mapped to different address in the real RAM. So there's no actually conflict. There's no conflict. As long as you could perform a good mapping, then there won't be any conflict. So the third problem can be also perfectly solved. And then another question we want to think about. So suppose you always want to, for example, if you want to read address 1024, also want to read and read to the memory address 1024. So do you always want to map them to the different location? So the answer is no. So a good example is, suppose you are you have a big file in your Outlook application, and you save it somewhere, right? And you want to save it somewhere, and you want to use that file again in your browser. So you could have a lot of different applications. You could have an email app. You could have an email program, a browser program, a video game program. So maybe many of those programs, they could share some data. They could share some data, right? So in reality, there are a lot of data shared by different applications. So if you would like to share certain data by different programs, then of course you do not want to map them to different location. So at certain situation, we would like to map the same data. We would like to map the same data to different programs, such as the black line here. So the program 1 and 2 may map to the same location. So may map to the same location if you are trying to share a piece of data by both of them. So so this is in general how we solve the 3 different questions, the 3 different problems for using the RAM. So we can actually use virtual memory technique to solve all those problems of RAM. And then how can the virtual memory work? How we actually perform the mapping? So this is the next video. So I'll stop here and record another video for the next part.